One of the biggest challenges in our digital world is just staying online. Every app, every website, every single service is in this constant battle against downtime. So today, we're going to break down the science and the strategy behind winning that battle, the quest for system availability. Okay, so picture this. When you first build any system, the goal seems pretty straightforward, right? You design it to handle a certain amount of traffic, a certain number of users, and it works. It's this perfectly oiled machine, totally ready for business. But then success happens. And that brings a whole new kind of problem. More users start flooding in, traffic spikes at times you'd never expect, and all of a sudden that well-oiled machine, it starts to choke. Pages load slowly, requests start to time out, and eventually the system just can't keep up. This is the exact moment every engineer dreads, and it's the core problem we have to solve. So how do we actually fight back against downtime? Well, you have to start by defining the goal. You have to quantify what staying online really means. And in the world of system design, we call that concept availability, and we usually measure it in nines. At its heart, availability is really just the percentage of time your service is up and running the way it's supposed to. It's pretty much the most important metric there is for reliability. So when you hear someone say their system has high availability, they just mean it has a ridiculously high uptime percentage. And this is where it gets really interesting. Look at how a tiny little change in that percentage translates into real-world time. 3 nines, or 99.9% availability, sounds amazing, right? But that still allows for almost 9 hours of downtime over a year. But push that to 4 nines, 99.99%, and you slash that downtime to under an hour for the entire year. And just look at that number for 4 nines per day. 8.6 seconds. That is all the downtime you are allowed in an entire 24-hour period to maintain that standard. That's your entire margin for error. It just shows you how incredibly demanding this quest for high availability really is. So you're probably asking, how is that level of uptime even possible? Well, it's not magic. It's all about architecture. Engineers use a very specific toolkit of patterns and strategies to build resilient systems that can actually stay online. Let's dive into those essential tools. This right here is a brilliant way to understand the first and maybe the most fundamental concept, horizontal scaling. Just imagine your server is a coffee machine. When one machine gets totally overwhelmed with customers, you don't try to build a single impossibly fast super machine. No way. Instead, you just add more machines and more baristas to share the work. In system design, that's exactly what we do. We add more servers to handle the load. Okay, but once you have all those servers, how do you decide where to send all the incoming customers or traffic? Well, that is the job of a load balancer. It's basically the manager of the coffee shop, pointing people to the next free barista. It spreads the traffic out evenly. It constantly checks if any server is feeling a little unhealthy. And if one is, it takes it out of rotation. It makes sure no single server gets buried. Now, what happens if a server actually crashes? That's where failover strategies come in. With an active-passive setup, you've got a backup server just sitting there, waiting on the sidelines. If the main one goes down, the passive one jumps right in to take its place. But in an active-active setup, both servers are working all the time, sharing the load. If one fails, the other one just keeps on trucking. It's already up to speed. And this exact same logic applies to your data. With master-slave replication, one database, the master, handles all the changes, and those changes get copied over to the other slave databases. If that master fails, you can at least still read data from the slaves. In a master-master setup, both databases can handle changes, which gives you even more resilience. Each one of these patterns is just a clever way of building in redundancy to avoid a single point of failure. But here's the catch. All this distribution, all this redundancy, it actually creates a fundamental conflict. It turns out you can't have everything. And this brings us to one of the most important ideas in distributed systems, the CAP theorem. And it forces us to ask a really hard question. When your system is spread out across a bunch of different machines and the network connecting them breaks, can you really guarantee both perfect data and perfect uptime at the same time? Well, the CAP theorem's answer is a hard no. The theorem lays out 3 guarantees. First, consistency, which means everyone always sees the most recent data. Second, availability, which means the system always responds to you. And third,
partition tolerance, which means the system keeps working even when parts of it get disconnected from each other. And the unbreakable rule is this: you can only pick two.
Now, here's the thing about the real world. Network failures happen. They're unavoidable. We call those failures partitions. And that means partition tolerance isn't really a choice, it's a requirement. So the real decision every architect has to make is this. When the network breaks, do you prioritize consistency or do you prioritize availability? Do you serve up potentially old data just to stay online, or do you return an error to make sure the data is perfect?
But as the guy who actually created the theorem, Eric Brewer, points out, it's not always a harsh all-or-nothing choice. The real goal is to find the right balance for your specific application. A banking app? It might sacrifice a little bit of availability to get perfect consistency. A social media feed? It'll probably do the exact opposite.
So all these architectural choices we've been talking about, they have a real mathematical impact on your final uptime. You can actually calculate how it all adds up. Let's take a look at the blueprint. So when your different services depend on each other in a sequence, like service A absolutely has to call service B to work, their potential for failure actually multiplies. To find the total availability of the whole chain, you have to multiply their individual availabilities together. And this is where it gets a little scary. Let's say you take two services that are each 99.9% available. That's 3 nines, which is pretty good. But if you chain them together, your total availability actually drops to 99.8%. Every single dependency you add in a sequence makes your whole system more fragile. But what about all those patterns we talked about, like redundancy and failover? Well, when you have components running in parallel, the math completely flips. Now the system only fails if both of them fail at the exact same time. This formula calculates that much, much smaller probability, and it gives you your new total uptime.
And wow, this just shows you the incredible power of parallel design. Those same two services, each with 99.9% availability, when you put them in parallel, give you a combined availability of 99.9999%. That's 6 nines. By building in that redundancy, you can create a system that is way, way more resilient than any of its individual parts.
So from measuring the nines to calculating the probabilities, this quest for uptime is so much more than just adding more machines. It's about smart architecture, it's about redundancy, and it's about making deliberate, sometimes difficult, trade-offs. And it all boils down to one fundamental question. For what you're building, what's more important? Perfect data or perfect uptime? The answer to that will define everything about your system.